Eighth lecture on advanced quantum mechanics is probably going to be the last lecture of this series. In the last class, we have introduced the perturbation theory. The theory was applied to first order cases or first order correction to the wave function and energy. Especially we are interested in getting the correct first order correction to the energy. And the theory is said to be time independent perturbation theory, as the interaction H prime or the perturbation Hamiltonian H prime does not depend on time. So it is, in that sense, it is time independent perturbation theory. And furthermore, it is said to be non-degenerate perturbation theory, as the states are assumed to be non-degenerate. If the states involved if we consider the degeneracy of the states involved, the calculation becomes a bit complicated. So we are avoiding all these things. So we have discussed the time independent perturbation theory as applied to non-degenerate cases, and we restrict ourselves to the first order theory only. And in the earlier lecture or introductory lecture, we have applied the theory to a small perturbation when applied to a particle within a box, and applied different cases in connection with the anharmonic oscillator, and we use the completeness of the wave function as well. Today we shall apply the theory to get the first order correction to the energy due to relativistic correction. By first order correction, we mean the energy that we get that we shall get in this class is correct up to the order V by C. We start with the hydrogen atom Hamiltonian. The Hamiltonian is H plus is equal to H0 plus a perturbation H prime, where H0 is splitted up into the kinetic energy part and potential energy part. The kinetic energy operator is P square by twice m, and potential energy is minus JD square 4 pi by 4 pi epsilon 0 r, where we have introduced the fine structure constant. Fine structure constant is a dimensionless constant, universal constant, which is the ratio of the speed of electron in first orbit to speed of light in free space, and it is its expression E square by upon 4 pi epsilon 0 h cross c, and its numerical value is approximately 1 upon 137. In that case, we have replaced this in there. And as per relativistic theory, there are three corrections, first order corrections to the energy. This is one. This is the correction to kinetic energy, correction term, which we have discussed earlier, and showed that wherever we expand the relativistic energy expression for the first free particle, first term is mc square, is the rest mass energy, second term is the non-relativistic kinetic energy, and then the term that comes as the kinetic energy correction term. Then the term comes as the spin orbit interaction term. Spin orbit interaction term is given by Z e square by 4 pi epsilon 0 1 by r cube L dot s. This term actually originally known as a spin orbit correction term or spin orbit energy. This arises due to the interaction of the electron spin dipole moment. This is the electron spin dipole moment mu s of electron, which interacts with the magnetic field produced by the orbital motion of the electrons. So this is due to this interaction term. And third term is known as the Darwin term, which is the correction to the kinetic and to the potential energy. Pi h line square So this is LS coupling term, and this is correction to potential energy, known as Darwin term. We shall calculate the energy, first order correction to energy corresponding to each of these states. Firstly, we write h1 prime is equal to p to the power 4, then 8 m cube c square. This we write minus 1 by 2 m c square and p square by 2 m whole square. So this is the term, and this part is simply t square minus 1 upon 2 m c square t operator square. If we see the t operator square can be written as h0 is equal to t plus b. So we can write it minus 1 upon 2 m c square. This is h0 plus or minus b, sorry, h0 minus b, because h0 was t plus b, and so t is equal to h0 minus b, and for b we write this part. So this is equal to minus 1 upon 2 m c square h0 plus z alpha h cross c upon r is this term. The corresponding correction term is this. Delta E1 is equal to, since there is no spin involved, we can write the unperturbed state as this NLM, and then this is H1 prime psi of NLM 0, which in this case comes out to be minus 1 upon 2 mc square then sorry, this should be squared, h0 plus z alpha h cross c by r whole square operating on psi NLM 0. This is equal to psi NLM 0 times, this is h0 square first term plus twice z alpha hc and then h0 and r. h0 commutes with r because h0, so we can write it as 1 upon r h0, then it is z alpha hc whole square 1 by r square, whole thing operating on psi NLM 0. Now H0 operating on psi NLM 0 gives you En0 times psi NLM, where En0 is minus half mc square, where half mc square z alpha square finds structure constant upon n square. So En0 this is Bohr energy as per Bohr's theory or as per Schrödinger non-relativistic theory. So when we operate, this is E0 square. So we write it as En0 square, then this is plus 2Z alpha HC En0 1 upon R plus Z alpha HC whole square 1 upon R square psi of NLM0. So this is, oh sorry, I have missed, minus this term, minus 1 upon 2 MC square term so this is equal to minus 1 upon 2 MC square, then first term is En square, then this term is twice Z alpha H cross C En0, and then 1 by R is sandwiched between these two states, which is the expectation value of R in the state NLM. And finally this term Z alpha H cross C, and this is 1 by R square expectation value in the state NLM. Now we know that 1 by R, the expectation value of 1 by R in the state NLM is Z bore radius N square 1 by R square NLM is Z square A0 square N cube L plus half. Another quantity will be required is that 1 by R cube expectation value. This is Z cube, A0 cube, N cube, L into L plus half into L plus 1. These are the three expectation values. Here we require two expectation value. One is this and the second is this. On comparing this, it comes out to be finally it when compiling all these things and on simplification, which I am just avoiding this complicated algebra, Z alpha by N whole square, and then we have 3 by 4 minus N into L plus half. This is the first order correction to the energy. This is first order correction to energy. E1 prime is equal to minus En0 Z alpha by N whole square 3 by 4 minus N into L plus half. This is the first correction. Now we come to the term this is the correction term due to kinetic energy. Now we come to the correction term due to spin orbit interaction term. Now spin orbit interaction term H2 prime is written as this: z e square by 4 pi epsilon 0 r cube L dot s. First thing, we write e square by this, we write as z alpha h cross c by r cube, and there is half factor, and this we write j square operator minus L square operator minus S square operator. Here we have written that j is equal to L plus S, so j square is equal to L square plus S square plus 2 L dot S. So L dot S, this minus these two divided by 2, and we write it as some factors xi of r j square minus L square minus S square, where xi is this part. So the correction to the energy term is E2 prime is equal to, here you consider since spin appears through J, we state the state as NL ML MS 0 state as, and we do not specify S because S is half for electron. So what we have is Z alpha H cross C by 2, or we write it as this. When this operation this, we get j into j plus 1, so this is, we get h line square is common, and then we get NL ML MS 0, then xi is there, xi of r is there, and then j into j plus 1 minus L into L plus 1 minus S into S plus 1, then this states as psi and ML MS 0. Now you see that j has two values. J is equal to L plus S. So the angular momentum quantum number for j will range from L plus S to L minus S. For electron it is L plus 1 to L minus 1. When L is equal to 0, this value is not allowed for L is equal to 0. So this is the restriction, that J ranges from L plus S to L minus S, that is J is equal to L plus half and L minus half. There are two values. And this, so we have H line square then xi, within xi we had the constant factor Z alpha H cross C by 2, and then we have psi and ML MS 0 1 by 1 upon R cube psi and L ML MS 0. and this is the expectation value. This is actually expectation value of 1 by r cube, 1 by r cube in the state NLM, which we have already quoted over there. And on simplification, this result comes out to be minus En0 z alpha square twice NL L plus half L plus 1 times L for j is equal to L plus half, and minus L plus 1 for j is equal to L minus half. For a state L is equal to 0, so j is this, and this correction term is 0 for a state, which we see that E delta E2 is 0 for a state. So there is no relativistic less troubling term for a state. Obviously here L is 0. So En0 z alpha square, sorry, this is z alpha whole square, z alpha whole square to NL L into half into L or minus L plus 1. Now for thirdly, we have to consider the correction term to the energy due to correction in potential energy, that is the Darwin term. H3 prime is pi H line square by 2m square c square times z e square by 4 pi epsilon 0 delta of r, which can be written as this part is written as z alpha h cross c delta of r, and the corresponding correction term is, here we need not to consider the spin part explicitly because the interaction doesn't have any spin dependence. When this we operate, you see that this bracket notation integration over entire space is implied. So we have pi h line square 2m square c square z alpha ac, and this becomes psi nlm at 0 modulus square, because this here we have used the fact that f of r delta of R integrated over entire volume V is F at 0. This is the property. And and using this on simplification, this becomes minus E n 0 Z alpha square by n, Z alpha whole square by n. So these are the term. Now let me write, this is the third term. So we write all this term, delta E correction, first order correction, this is delta E1 plus delta E2 plus delta E3. All these three correction term contains Z alpha square, so minus E n 0 Z alpha whole square. Then from the first term it is 1 by n square 3 by 4 minus n into L plus half. This is the first term. From the second term we have two NL multiplied by either L or minus L plus 1, and then third term is plus 1 by n. If we combine this term, simplify this, we get minus E n 0, then 1 plus Z alpha by n whole square times n by j plus half minus 3 by 4. This is the first order correction, correct up to V by C square term. So this is the correction term. You see that the energy depends on N as well as on J. So when we shall discuss the spine structure of hydrogen atom, we shall directly use this expression. So here we have seen an example where the perturbation theory has been applied to calculate the fine structure energy correction to hydrogen atom. The same perturbation theory could also be applied to an hydrogen atom when subjected to an electric field. Say we have applied an electric field which is along K cap E, and then it accounts for an interaction. That interaction part is actually it is E dot Z type interaction. It is because whenever an electric field is applied, the charge separation occurs, and due to charge separation a induced dipole is created, and this induced dipole interacts with the electric field. So the potential will be of the form E times Z. If we apply perturbation theory, we will get the shift in energy as is found in Stark effect. Stark effect is the shift in atomic energy levels when the atom is placed in a static electric field. Another thing happens whenever an atom is placed in a magnetic field, the atomic electrons, as it revolves around the nucleus, they constitutes a dipole, and this dipole interacts with the magnetic field as created by the electron. Whenever one looks at the situation from electron's reference frame, it finds that the nucleus revolves around the electron. So this charged nucleus creates a magnetic field, and this magnetic field interacts with the dipole moment of the electron, and this this gives rise to an energy shift, which is known as the Zeeman effect. Zeeman effect may arise from three different considerations. When the electron has only orbital angular momentum, then there is no spin part, and this gives rise to normal Zeeman effect. When there is only spin part, no orbital angular momentum part, this is the situation what was observed in Stern-Gerlach experiment. And when we have the atomic electrons have spin as well as orbital motion, we found that anomalous Zeeman effect arises. In a Zeeman effect case, the H prime actually originates from mu dot b, and this is effectively becomes b, and if we consider the angular momentum operator, it's z component when b is applied in z direction. So we can also calculate the corresponding energy shifts due to this interaction, which gives rise to Zeeman effect. Zeeman effect. So Zeeman effect is the shift in atomic energy levels when the atoms are placed in a magnetic field. That's all about the application of perturbation theory, and in the next class we shall start the spectroscopy.